this video, we are going to learn on the limiting and excess reactants. A limiting reactant or limiting reagent by definition is the reactant that is completely consumed in a chemical reaction, while the excess reactant is the reactant that is still unused or left after the chemical reaction has been completed. Okay, when there is not enough of reactants, let's say here we have the limiting reactant, so the reaction will be stopped. Example here, when we have 4 tires plus 2 headlights to produce 1 car. Okay, tires and headlight here we consider as the reactants, while the car here we consider as the product form. Let's say you are given 20 tires and 16 headlights. So how many cars that we can produce from this number of reactants? Okay, 20 tires divided by 4, so we can produce 5 cars, while 16 headlights divided by 2, we can produce 8 cars. So comparing both of the number of cars that we can produce, we can say that tires is the limiting reactant. Okay, we can only produce 5 cars. 5 times 2 headlights, so we only need 10 headlights in this case. So we have extra of 6 headlights. So in this case, headlights is the excess reactant. Let's take a look at another example here. In one process, 124 grams of aluminium are reacted with 601 grams of iron trioxide to produce aluminum oxide and iron. So the question here is number 1, to determine the limiting reactant and excess reactant, and number 2, calculate the mass of aluminum oxide form. First thing first, we have to write the chemical reaction involved. So here we have the aluminium and iron trioxide as the reactant, and the product form here aluminum oxide and iron. Okay, so what we need to do next is that we have to calculate the number of moles for aluminium. So the formula that we need to use is mass divided by molar mass. So the mass of aluminium is given as 124 grams divided by 27 grams per mole. So we can get this from the periodic table. So the moles for aluminium is 4.59 mole. Next is that we need to calculate the number of moles of iron trioxide. So the same formula here. So we substitute the value of the mass, 601 grams, and we have to calculate the molar mass for the iron trioxide, where the molar mass is equal to 160 grams per mole. And the number of moles for iron trioxide here is 3.76 mole. In a chemical process, please bear in mind that we also need to balance up the chemical equations. So looking at the reactants and the product form here, we can see that the product here is aluminum oxide. We have 2 atoms of aluminum and 3 atoms of oxygen. Okay, looking at the reactant here, we have to put 2 at the front of aluminum. So here, since we have the same number of atoms for oxygen, so just remain like that. And then looking at the iron atom here, we have 2, so we have to put 2 at the front of iron. So overall chemical equation is already balanced. So what we need to do next is that we have to find the number of moles of aluminium based on the balanced chemical equations. So this one is the number of mole that we get earlier, 4.59 moles. So we have to divide by 2. 2 is the coefficient from the aluminium. So we get the new number of moles of aluminium here is 2.295 mole. And next is that we have to find the number of moles of iron trioxide based on the balanced chemical equations. So here we have the mole earlier, 3.76 mole divided by 1. 1 is the coefficient for iron trioxide. So we also get the new number of mole here, 3.76 mole. So what we need to do next is that we have to compare both number of moles. Okay, the smallest number of moles indicate the limiting reactants, and the largest number of moles indicate the excess reactants. Okay, comparing both of these number of moles, we can say that aluminium is the limiting reactants and iron trioxide is the excess reactant, because this number of mole of iron trioxide is much greater than the aluminium. So how about the mass of aluminum oxide form? In this case, we have to actually relate the mole of limiting reactants with the mole of the product form. So we have the balanced chemical equation with the right stoichiometry. So to figure out the amount or the mass of the product form, it must be determined from the limiting reactants, okay? Because the limiting reactant is the one that is used up to produce the product. So we have to relate this. 2 mole of aluminium, okay, producing 1 mole of aluminum oxide. So here we have 1 mole of aluminum oxide. Earlier, we have calculated the number of moles of aluminum is 4.59 mole. So how many moles of the product form, okay, for the case of aluminum oxide? So we have to crisscross, okay, multiply. Then we get X equal to 4.59 mole times 1 mole of aluminum oxide divided by 2 mole of aluminum. So we get the mole of the product form is 2.295 mole. Next, that we have to find the molar mass of aluminum oxide. Okay, so this one is already calculated. So the molar mass of aluminum oxide is 102 gram per mole. So to find the mass of aluminum oxide, we have to multiply the mole and the molar mass. So we get mass of the aluminum oxide here 2.295 mole times 102 gram per mole. So we get the mass of the product form here is 234 gram. Next, I'm going to show you how to find the reaction yield. But first, we have to understand what is reaction yield. Reaction yield is actually a measure of the quantity of moles of a product form in relation to the reactants consumed. So usually the reaction yield is expressed as a percentage. So here we have the theoretical yield, actual yield, and the percentage yield. The theoretical yield by definition is the amount of product that will be formed if all the limiting reactant is consumed. So this one is based on the chemical equations from the process. So this one is theoretical only. So the actual is actually the reality, where the amount of product that obtained from a reaction is always less than the theoretical yield. Okay, this one is the reality from the chemical process. So we have to find the percentage yield by using this formula, where this is the proportion of the actual yield to the theoretical yield. So we have to also times 100% to get the percentage. Let's take a look at this example where we have 15.6 gram sample of C6H6 reacts with excess HNO3 to produce a 13.8 gram of C6H5NO2. So from the question, we already know that HNO3 is the excess reactant while the C6H6 is the limiting reactant. So what is the percentage yield of C6H5NO2? So first thing first, we have to write the correct chemical equation with the correct stoichiometry. So this chemical equation is already balanced, and we extract the information from the question where we have here C6H6 of the limiting reactant having a 15.6 gram of its mass, while the product form having a 13.8 gram. Okay, so what we need to do first is we have to find the number of moles of C6H6. So we already have the mass, so we have to divide the mass by the molar mass. Okay, how to find the molar mass? We have to get it from the formula here: 6 times 12 for carbon plus 6 times 1 for hydrogen. So we get 78 gram per mole. Okay, so here we have the number of mole for C6H6 is 0.2 moles. Next is that we have to find the number of moles of the product form, which is C6H5NO2. So we have to relate the number of moles of the reactant, of the limiting reactant here, 1 mole of C6H6 to produce 1 mole of C6H5NO2. So here we have 0.2 moles of C6H6. So how many moles of the product form? Okay, so we have to calculate by using this. So we get the X mole of the product form is also the same 0.2 moles. Next is that we have to find the theoretical mass of the product formed here. Okay, so we have the moles, so we have to calculate the molar mass for the product. So here we have the molecular formula for the product form, so we can get the molar mass. So mole multiplied by the molar mass, we get the theoretical mass of the products form, 24.6 grams. So to find the percentage yield, we have to use the formula where the actual yield divided by the theoretical yield times 100%. So here is the actual yield. Okay, so when we divide the actual yield with the theoretical yield, we get the reaction yield is actually 56.01%.